Okay, we're going to talk a little bit about volume by discs, which is what we did already. This comes from Larson 6.2, which is coincides with lesson 80 from Saxon, which is going to be on your quiz on Monday if we have school. Anyway, one of the things we looked at is the volume is pi r squared times the thickness if it's rotated about the x-axis, and r squared dy if it's rotated about the y-axis. And we did things like this. We had find the volume of a solid form by revolving the region bounded by this function. And here we get this. We revolve it around the x-axis and it gets like a football. Notice those revolutions are going to be circles when I slice it, and so I've got pi r squared dx, and I need to find out what my a and b are, and they happen to be 0 to pi. If you don't know, set these equal to 0 and solve for x. Now my radius goes up, so that happens to be what f of x is. I square it, and I get sine x. The rest is a pretty straightforward integration. And plug in my limits, and I get 2 pi. Okay, in the second example, we're going to find the volume of a solid form by revolving the region bounded by the 2 minus x squared. Okay, so now what we have here is that we've got this y equals 2 minus x squared and this line y equals 1. And we want to revolve it around the y equals 1 line. And so I'm going to get a solid that kind of looks like a football, but I have two different radius. So what I want to know is find out what this difference is. So I'm going to subtract the two. And that's what I did down here. So I subtracted the top one minus the bottom one, and I got that my radius is 1 minus x squared. To find my limits, I set the y's equal to each other and found my x limits to be plus and minus 1. So now I can set up my integral using discs. So what I've got here is I want the volume of pi as it goes from -1 to 1 of r squared. Multiply it out, take the integral, plug in my limits, and get my value. But what happens if we have an object with a hole? For example, we have something that looks like this, and there's a hole in it. How do I find the volume of a hole? Well, typically when we've done areas, we've actually said the area of the big minus the hole to get the area that's left. So now what I have is I'm looking at the volume of the r outer thickness, the radius on the outside, minus the radius on the inside, times the thickness of my disc. And we tend to call this volume by washers. And we would actually put volume as pi r outer squared from the limits minus pi r inner squared. This just stands for outer, and this is the inner. You can call it whatever you like. So this is basically the volume of the hole. So now we're going to look at, if you want to, look at some pictures in Larson, and they'll show you some nice 3D. Here we have an example of a volume that's bounded by y equals square root of x, y equals x squared, and the x-axis. And so what I did was I drew what I have. And if you'll notice, this is the square root, this here is the parabola, and I'm going to rotate it about the x-axis. And in very light hash marks, it would kind of look like this bowl, not quite a cone, but very close to a cone. And what we have here is we have what I would call our outer, and this is our inner. So our outer is the square root of x, our inner is x squared. If I want to know what those limits are, now I'm doing this with respect to x, so I need to know my limits. And I have the limit 0 and 1 by setting them equal to each other. And so now what I have here is a volume of pi r outer squared minus pi r inner squared. Simplify these, and if you'll notice, the integrations aren't that difficult. We come down, we plug in our limits, and we get 3/10 pi. The hardest part is going to be making sure we don't lose our signs if we happen to do this in a no calculator portion of a test or a quiz. Otherwise, you could put this in your calculator and get the actual number. but leave it in pi form if it says without a calculator. Now we have another example. We're going to look for the volume formed by revolving the region bounded by y equals x squared plus 1, y equals 0, x equals 0, x equals 1, and we're revolving it about the y-axis. So again, you don't always have these pictures, so you have to be able to draw them. So that's what I did. I've got the line x equals 1, I've got y equals 0, and I've got y equals x squared plus 1, and we want this area. So if you'll notice, if I want to know what my limits are, because I drew my rectangles this way, and I'm revolving it about the y-axis, I need a dy. So I know here is my y value, and how do I find this y value? Well, to do that, I just plug in 1 into my original, and I get 2. So now what I'm going to do is I've got my R outer, and I'm going to do it in pieces. So I've got this bottom part is just going to be a radius of 1. So going from 0 to 1, 1 squared dy, and then what I have here is the 1 squared minus the R squared to get this radius. And this one's going to go not from 0 to 2, but it is going to go from 1 to 2. So this is a 1. So now this integration is pretty easy, and I end up with pi. I take this and I have 1 minus a square root squared, and I had to solve for y, by the way, because they gave it to us in y equals. So when I solve for y, this is what I get. And then I square it, and I end up with y minus 1. So 1 squared minus 1, again, this is a 1. And so I took it in pieces, found this volume here, that's pi. I have to integrate this, which is a pretty straightforward integration. I apologize for the messy writing. Basically, we have minus y squared over 2 plus 2y. When I plug in 2, I get a minus 2, positive 4, this is a positive 4, minus a negative 1/2 plus 2. And as I simplify, I get 3 pi over 2. Here's an application. We have a manufacturing where a hole is getting drilled into a sphere. The sphere has a radius of 5 inches. The hole is a radius of 3 inches, and we want to find the volume of this metal ball bearing or whatever you want to call it. So as I draw my picture, this is my hole. So here's my sphere. And a sphere, when I slice it in half, is just a circle. So the equation of this line, this top part, is y equals square root of 25 minus x squared. And my R inner is 3. And what I have here is this lovely little volume. There's a hole that goes all the way through here. And since I'm going to talk about rotating it, I'm going to ignore this part, find this volume as I rotate it, and I will have the volume of this metal. Now the sphere, like I said, is a circle. And so I found my R outer is square root of 25 minus x squared. My R inner is 3. To find my limits, I set them equal to each other and solve for x. So it goes from minus 4 over here to plus 4. And now I'm going to find the volume of the outer, pi, a to b, R outer squared minus R inner squared. I plug in my limits. And I have 25 minus x squared minus 3 squared. I get 16 minus x squared. The integration is pretty simple. Plug in my values. Be careful of your minus signs. And I end up with 256 over 3 pi inches cubed. Because they gave us inches, you need to make sure you put units. You don't want to lose a point on that. I realize that in the real world we would multiply by pi and get a number, and that's fine as long as it's not a no calculator portion. All right, now you should be able to do lesson 90. You can follow the examples that I put on the notes. You can also look at Larson book. So keep working on your homework, and we can talk more about this. Obviously, volumes by washers will not be on the quiz.